You're welcome to day 31 of 50 days of tutelage. In this class, we will be talking about mappings and functions. So, what is a mapping and what is a function? Before I give you any proper definition, I want to take you back a little bit to when you were in kindergarten because that was exactly when you started working with mapping. Once I show you now, you are never going back to forgetting about it. You remember those times that you'll be given an assignment, something of this nature. They will say, trace the lines and match the animals. So what you do is that you look at the animal, you try to identify it. For instance, now this first one now is a zebra. So you trace a line and then you trace it to this place. This second guy is a turtle, so you can trace the line and match it with this. This one is an elephant, so you go ahead, you do that. Then you have this one is octopus, and finally you have the lion. So what you have done in this place is that you have actually mapped the image. These guys, you have mapped these images, you have mapped it with the names of the animals. So the animals are here on the left hand side and their names are here on the right hand side. So you have correctly mapped them to each other. And that is exactly what mapping is in mathematics as well. The only difference now is that in in mathematics, we deal more with things that can actually be properly structured. Yes, they can actually be properly structured. For this as well, it is actually structured. It actually follows the entire definition of mapping. For instance, the mapping is actually defined as a rule that assigns elements from one set to other elements in another set. And this actually goes well with that definition as well. So, because when we are talking about mapping, you are actually going to be dealing with two sets. There's going to be a set one and there's going to be a set two. So, when you look at this example now, this is your set one and this is set two. And what do we call set one? Set one is actually called the domain. Set one is called the domain, and set two is called the codomain. So, what happens from the domain is that the domain is where you pick the element from, the element you want to act upon. You pick them from the domain. So, if a mapping is a rule, so whatever rule it is that you're applying, the rule is going to be applicable on elements that belong to the domain. That is the first set. Now, so here's the thing. After the rule is done acting on the element that you pick, you produce a new element. This new element, you always find them in the codomain. So in the case of this now, the rule is that you trace the lines and match the animals with their correct name. So which implies that when you see the picture of an animal here, the new thing that will happen is that when you get to this place, you are matching it with the name of the animal. So you can see that this mapping is a map that actually assigns the pictures of animals to their names. So in that situation, the picture of an animal belongs to the domain, while the name of those animals belong to the codomain. And this is generally what mapping is all about. But I've been able to explain what domain is and I've been able to explain what codomain is. What is now such that if you have, let's say in this case now, after you have done all this mapping now, there are still some guys left here. For instance, let's say I put a snake here. Yeah, so let's say there's a snake here. As you can see, you don't have a picture of a snake in this place. So therefore, snake will not be mapped to. But even though snake is still in the code domain, elephant, lion, octopus, zebra, turtle, and snake, this set constitutes the code domain. So for everything that is in the other side, they will constitute the code domain. But if it happens that you are able to map to some element and you leave some elements out, those elements that you map to now, they now take a special name known as range. They take a special name known as range, which implies that in the codomain there is another set, and this set is a set that contains every element that has been mapped to. So, but the codomain is the general set. Is the general set that gives the elements that can be mapped to. But when you have when you are done mapping, all the elements that are mapped to, they form a new set called the range of that mapping. So the range of that mapping are all contains elements that are what? That are mapped to. And that's basically what mapping is about. Now, what is now function? You see, mapping can be done anyhow. Mapping can follow anything. So mapping does not really like uh, really put so much restriction like that. But the moment we get to what we call a function, function has a restriction. Function is a type of mapping actually. Function is also a mapping. It's just that function has its own restriction. And the restriction is that for every input that you pick, there is exactly one output. That's the restriction. That is, if there is, you pick this guy now, it can only have one output. It can only have one output. So the moment you pick one thing and it has more than one output, then it is not a function. This is still a mapping. This is still a mapping. So a mapping generally just assign them from the left to the right. But in the case of a function, when you pick one thing from the domain, so proper way to define a function is that a function is a special type of mapping such that any element that is picked in the domain is assigned to only one element in the codomain. You cannot assign one element from the domain to more in the codomain. That is what defines a function. So if I pick 2 in the domain, if it is going to be a function, and let's say it has given me a kind of result of 5, that implies that for every time I put 2 into that function, I must always have a 5. I cannot have any other number. However, here's where this thing actually gets very twisted. You can actually also have several things in the domain, and then you have these two in the codomain. So I think I should use a different color for them. So you have these two things in the codomain, and then you have a mapping of this nature. This goes to this goes to this, and this goes to this. This is one this is one dynamic. This is also a function. That's number one. This is also a function because, as you can see, this first element here is mapped to one element. This second element here is mapped to one element. So the rule prohibits us from mapping one element to many. So we cannot do one to many. But we can do many to one. So a function prohibits one to many, but it permits many to one. So take note of that. And also, the second thing you need to take note about a function is that if you have defined the domain of a function, so let's say the domain is defined as A, B, C, and D. Now, let's say we have a codomain here, and this codomain contains 1 and 2. Now, a function can be defined in this way. So you can have this to be a function. So it goes this way, it goes this way. Now, what you notice here is that I've been able to map almost everything here to everything in the codomain. So please, every time on the left, I will always be writing the domain, and on the right, I will always be using the codomain. So in case I don't label it further, left domain, right codomain. A function does not allow you to not map something from the domain. For every time you have a function, you must always map out from the domain. Nothing is allowed to remain unmapped from the domain. However, you can actually have stuff in the codomain that are not mapped to. So take note of that. You're not allowed to leave an element unmapped out in the domain, but you are allowed to leave an element to not be mapped to in the codomain. So what am I talking about? So if you notice this now, this what I just drew, the thing I just draw now, it is not a function. It is not a function. Why? Because D, A, B, C has been mapped out, and they follow the rule. That is, you have what? Many to one and all of those things. But unfortunately, D does not have anything in the codomain. So therefore, this is not a function. So if I want to make this a function now, so what can I do? I can still say D goes to this. Now with this now, we have a function because everything in this place is mapped out, and also not a single one from the domain is mapped to many, but we have many to what? To one. So this is a function. In fact, let me also shock you of what else can also be a function. Do you know that I can decide to map this to this and map this to this? This is still a function. Yes, I'm leaving two out. So a function does not really care much about the codomain. Like I told you, that's why we have what we call range. So it does not necessarily have to cover everything as long as it's being mapped out. So where it is necessary for you to cover everything is in the domain. That is where you have to cover everything. And this basically describes what a function is. So a function is, number one, such mapping that allows you to do many to one, but you cannot do one to many. In a simpler term, a function is a special type of mapping where each input has exactly one output. Each input has exactly one output. And at the same time, whenever you determine the domain of that function, the function must be mapped out for every member of the domain. Once those two things are satisfied, then you say that mapping is a function. Now, we now have three types of function that I would like to talk about. A function can be a one-to-one function. A function can be one-to-one. This is also what we call injective. So if a function is one-to-one, it is called injective. A function can be onto. When a function is onto, we call it surjective. Surjective. And lastly, we have what we call a one-to-one correspondence. A one-to-one correspondence. In this case, we say the function is bijective. Actually, this third one is not really like anything special. It's just that it's the combination of these two together. So this third one is the combination of these. So if a function is both one-to-one and at the same time it is onto. So let me explain each of these concepts one after the other. What does it mean for a function to be one-to-one? It means that in this case, I had explained earlier that a function allows many to one. So, but this restriction now, if a function is one-to-one, the restriction is such that you cannot have many to one again. It has to be one input, one output. And once these two are already together, nothing else can be mapped to this guy. Unlike what I did here, so you can see that in this case now, I have many to one. But if A was already mapped to one, then B cannot be mapped to one again. That is when the function is a one-to-one function. So a one-to-one function, which is why the range of a one-to-one function is always the same thing as its codomain. So for example, if I have this here and I have another set here, so let's say in this place I have 1, I have 2, I have 3, and I have 4. And in this place, let's say I have 2, 4, 3, 1. So I want to do this mapping now. So this mapping, I can map this to this. I can map this to this. I can map this to this. And I can map this to this. So what you notice here is that this function right here is a one-to-one function. Is one-to-one. So just as the name implies, that is, Roman figure 1 matches with 1, Roman figure 2 matches with 2, Roman figure 3 matches with 3. So no such thing like, oh, more than maybe just more than one of these is being mapped to one of the things that you have here. So in this case now you have a one-to-one function, meaning that one element from the domain, one element from the codomain. So that is why in this place you cannot have a lesser cardinality of range. If the cardinality of the domain is 4, then the cardinality of the codomain has to be 4 as well. So or maybe more, but at least it has to be what? It has to be 4. So for a one-to-one function, the cardinality of the domain is also the same thing as the cardinality of the range. Cardinality of the domain is the same thing as the cardinality of the what? Of the range. Unlike when I describe many to one is such that what's the cardinality of the domain here? The cardinality is 4. If you don't know what cardinality is, I already talked about set. So go and check the previous classes to know about set. But in this case, what's the cardinality of the range? 1. I'm not saying 1 because like this is 1 here. Like the number of elements in the range is 1. So therefore, in this place, the cardinality of the domain is not the same as cardinality of the range. But when it comes to a one-to-one function, cardinality of domain must be the same as the cardinality of the range. Now, the next one is onto. Now, when is a function said to be onto? In this case, every element in the codomain will be used. So for instance, in this place, you can see that I have 1 here and I did not even make use of 2 as well. But in the case of an onto function, if the function is going to be onto, you cannot leave no man can be left alone. No man can be left alone. You cannot leave them alone. Which is why if it is going to be onto and it's going to also be a function, that means that the cardinality of the codomain cannot exceed the cardinality of the domain. What do I mean by that? Let me explain. So if you have this and you have this, I think I should just be using dots, dots, dots. So let's have a dot here, let's have a dot here, and let's have 2 dots here. Now I will start with 5 dots. 1, 2, 3, 4, 5. 1, 2, 3, 4. So let's see. If a function wants to be onto, it means that everything here must be mapped to. And from what you have known, if it is going to be a function, one of these can only have what? One output. But if I say every single one here has one output, let's start with that. Every single one here has one output. Now, it means that one of these will be left alone. Now, is this a function? Yes, it is a function. In fact, it is a one-to-one function. But if this function is going to be onto, this thing has to be mapped to as well. What does that mean? It means I am forced to now extend one of these to this guy as well. If I should do that, that will mean that there is one element in the domain which is mapped to what? Which has 2 different outputs. It has 2 different outputs, and automatically this is no longer a function. So which is why I explained that if a function is actually going to be onto, it means that number 1, you must have a what? A lesser element. The cardinality of the domain has to be exactly like the cardinality of the codomain has to be exactly the cardinality of the domain or lesser. So in this case now, if I, let's say, remove this last element here now, what you notice here is that this is actually a function, and everything in the domain in the codomain is being mapped to. So therefore, this function is onto. But at the same time, what do you notice? You notice that it is also one-to-one because it is one body from here, another body from here. They are just one like that. So this function is one-to-one and onto. In fact, it has already led me to the third guy, which is called what? A bijection. A bijection. If a function is both one-to-one and at the same time it is what? It is surjective. That is, if it is both one-to-one and it is onto, then you have what? You have what we call a bijection. So let me give you something that is purely onto and not one-to-one. So if you have something of this nature, so you have this, 1, 2, 3, 4, 5. Let's say you have this guy, you have 1, 2, 3. So in this case, if you have this map to this, 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 and you have this map to this. So you can see this guy still maintain a function. This input has only one output. 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 At the same time, everything in this place has been successfully mapped to. That is, nothing in the codomain is left behind. Therefore, this function is purely onto. It is not one-to-one because as you can see that there is 2-to-1 here, so it's not one-to-one. So this function is purely subjective and not what? And not one-to-one. So you need to be able to identify the difference between an injective mapping or an injective function, a surjective function, and a bijective function. So that is the basic introduction to what the different type of functions are. The next thing we want to discuss now is that let's now discuss function itself. You see, function, I've been able to describe the different element of function, but there are three things that makes up a very perfect function actually. Three things makes it up. So a function is first of all defined on a domain. Then after it has been defined on a domain, it dumps the element into the codomain. And to do all these things, it make use of a rule. So these three things, the domain of a function, the rule of a function, and the codomain of a function, these three things define a function perfectly. So if you're going to be able to analyze a function correctly, you will need to understand and be able to analyze these three things very well. So let's go right into it. I've explained the domain, I've explained the codomain. So I want to explain the rule of a function now. Of course, I will still talk more about the domain of the function, so we'll still go to that. Now, what is the rule? The rule is the common one. So for instance, let's say you are picking elements from the domain. Let's call those elements, let's call them X. In fact, their name is called pre-image. So we call this guy pre-image. So pre-image of the function. Then when you get it, you get element from here. Let's call those elements Y. This element Y, we call them image. So therefore, Y will be the image of X, and X will be the pre-image of Y. So when you carry the rule now, the rule is saying that Y, which is the image, is going to be equal to f of X. So this f of X, right, like this, is the rule. F of X is the rule. So you can say something like f of X equals 2x plus 3 over the domain, let's say you have 1, 2, 3, 4. And let's say the codomain now is from 1 to 15. The codomain is from 1 to 15. So what does that mean? I'm going to do this. F of 1 will definitely be 2 multiplied by 1 plus 3. So all I have to do is replace x with 1. So that will be 2 times 1 is 2, then 2 plus 3 is 5. Then I go again, f of 2 is 2 times 2 plus 3, and that is going to be 4 plus 3, which is 7. Now, if you go and do f of 3 like that, that will be 3 times 2 is 6, 6 plus 3, that will be 9. And then if you do f of 4, that will be 2 times 4 is 8, 8 plus 3, that's going to be 11. So, which implies that the images, so the image of 1 under this rule, the image of 1 is 5. The image of 2 is 7. The image of 3 is 9. And the image of 4 is 11. At the same way, you can say that the pre-image of 11 is 4. So this is the rule of the function. And this is the domain. And this right here is the codomain. So that is basically the rule of a function. So how do we now find the domain of a function? So if I give you a function, How do you know the domain? Because I can ask you to determine the domain of the function. So how do you find the domain of the function? Basically, the first thing you need to do is that you need to identify what type of function are you dealing with. What type of function are you dealing with? Now, we can have functions. You see, functions that are not rational and they don't have logarithmic, anything logarithmic in their nature or whatever. If such functions like a polynomial function, yes, polynomial functions, linear functions, their domain is always the entire set of real numbers. Like I said, if you have not, if you were not in the class for sets, when I discussed about sets of numbers, then you need to go and check it again. So polynomial functions are always of the form ax raised to power n plus, let's say a naught x raised to power n, a1 x raised to power n minus 1, and it goes on and on like that until you reach an. Linear functions are always of the form y equals mx plus b. So for this, their domain is always the entire set of real numbers. But you see, the moment you begin to have some special things, like let's say you have a function f of x equals square root of x now. Now, if you have a function f of x equals square root of x, so let's say for instance, I say y equals square root of x, then what I'm saying is that I can say that if I square both sides, that means that y squared is going to be equal to x. And from here, I have that y squared minus x equals to 0. Now, it implies that for every value of x that I pick here, I can actually substitute two values of y. And that implies that x from the domain now has two values of y. And from what we have already what we have already learned, you cannot have this thing to be a function. So therefore, you have to restrict this thing under a particular domain. And that domain is x is greater than 0. So anytime you have a square root in a square root function, to find the domain, all you have to do is to solve the inequality for x is greater than 0. For instance, now, if you have f of x equals square root of x plus 3, then if I ask you to find the domain of this function, all you are going to do is that say that x plus 3 is greater than 0. And that implies that x is greater than negative 3. When you have this, this is going to be the domain of that function. So any value that is any real number that is greater than negative 3 is going to be a domain of this function. And that's exactly how you find the domain of square root functions. Anyways, there's another way by the way, there's another way we represent this thing. X is greater than minus 3 means that you're going from negative 3 to infinity. If it was x greater than or equal to negative 3, oh yes, actually, it is actually greater than or equal to, yes, it is greater than or equal to, it can be 0 as well, it can be greater than or equal to, sorry about that. So if it is x is greater than or equal to negative 3 now, so you're going to have this negative 3 comma infinity. So you can see what I did here. In this place, when it is strictly greater than, I used, this is x is greater than negative 3. I used just the normal bracket. And when it is what? Greater than or equal to negative 3, I use the square bracket. So take note of that. So for anytime you want to find the domain of f of x equals to square root of a function, all you have to do is what? Is make sure that it is greater than or equal to 0. But when you have a rational function, so such that f of x is some p of x over q of x, your major responsibility is that the denominator cannot be equal to 0. So solve for the value of the denominator for which this is 0, and then any other thing will be in your domain. For instance, if you have f of x equals 1 divided by x minus 4, if you want to find the domain of this guy, the first thing you do is that you say x minus 4 equals to 0. That means that x equals to 4. So what you have done is that you have looked for the value of x that makes this guy undefined. So what you do is that you now partition the real number. You go from the left. You say anything x less than 4 or x greater than 4. They belong to the what? They belong to the domain. And how can you now express that? When you have or, it means union. I've explained this one under set. So it means that you have negative infinity to 4 union 4 to infinity. What you have done now is that you have excluded 4 in this entire thing. You have excluded 4. So that means that I'm going from negative infinity to 4. I will jump and move from 4 to infinity. So that will be the domain of this function. Of course, they can be a little bit complicated because you can have quadratic expression in the denominator and all of that. That is all you have to know is how to attend to inequality problem. I've already explained that in a previous video. In today's class, I'm only dealing with mapping and function. Now, how do you find the range of a function as well? It's as simple as anything. All you have to do is the possible values of what? The possible values of the function. That is the possible values of y. Like I've defined here the rule. The possible values of y. That will be the range of the function. Now, how do you now test a function when you have a graph of a function given? So for instance, if I have this set of graphs, one more, let me say we have something of this nature. Yeah, so if you have, no, that's not what I intended. So if you have this set of graphs, how do you know which one of them is a function? How do you know which one is not a function? You use what we call the vertical line test. So you draw several vertical lines on these graphs. You draw several vertical lines. If your vertical line is touching more than 1 point, then that implies that that thing is not a function. So this is not a function, this is not a function. This is a function, this is a function. So when vertical lines touch more than 1 point, then, and in fact, if it is only one of the vertical lines that touch more than 1 point on the graph, then that graph is not a function. So the next thing I'm going to discuss about function now, I'm mapping. I'm going to discuss about composite function, and I'm going to talk about how we can find the inverse of a function as well. I'm supposed to discuss about asymptotes and the likes. Maybe I'm going to discuss that in a separate video, which is why you actually need to like and subscribe to my channel so that when I drop any new video, you're going to have access to them. So I'm going to be ending it on composite function and inverse of a function. What is composite function? Composite function is such that in this situation, we have defined that y equals f of x. But imagine that I define another function. Let's say this one is y1, and let's say another function y2 equals g of x. So I cannot define a function y which is actually a function of another function. So more like you have f of g of x. This is what we mean as composite function, and oftentimes it is represented this way: f composite g of x. So you can see that I did not say f times g of x, so I use something like a little circle there. So what does this mean exactly? It simply means that, let's say y equals 2x squared, sorry, y1 equals 2x squared minus 4. That is our f of x. And y2 equals 2x plus 4. Why am I using the same numbers? Let's say 3x minus 1, or plus 1 rather. Now, this is going to be our g of x. If I ask you to find g composite f, meaning I want you to find g of f of x, what that implies is that you go to g. Everywhere you see x in g, you replace it with f of x. So this is our g. So instead of 3x, this is going to be 3 times f of x plus 1. And what would that be? 3. So what is f of x? That is 2x squared minus 4, then plus 1. So you can see how I am using parentheses to make sure that I distinguish everything properly. And if you like, you can expand this. This would be 6x squared. 3 times negative 4, that's negative 12. Negative 12 plus 1, that's negative 11. So, and that will be g of f of x. In the same way, you can find f of g of x, which means that f of g of x. So what do you do here? You also go to your f and you replace everywhere you see x there, you replace it with a g of x. So g of x is 3x plus 1. So therefore you have in this place 2 3x plus 1 all squared, then minus 4. So what do? You expand this, you multiply it with 2, then you subtract 4. Then that will be your f of g of x. That is what we mean by a composite function. So finally, inverse of a function. Inverse of a function. For us to be able to find inverse of a function, we always ensure we restrict it that the function has to be one-to-one. Why is it so? Because if the function is not one-to-one, if it is like, let's say, many-to-one now, like in this case now, inverse is simply me tracing this thing. If I've gotten my image, I want to trace it back to the pre-image. And if you are doing that now, that means that you are going to have this being mapped to 2. So therefore, that is not going to define a function. So if it's going to be a function, it has to be one-to-one so that I can easily trace from here to here and from there to here as well. So how do you now find the inverse of a function? So let's have a one-to-one function. Y equals 2x minus 3. Most linear equations, they are always one-to-one. So if this is a function, how can I find the inverse? What am I trying to say is that when I think I've used this particular function earlier, I've generated the images of some of it earlier. Oh, it was 2x plus 3. So I've gotten 1 to 5, 2 to 7, 3 to 9. Okay. 1 to 5, 2 to 7, 1 to 5, 2 to 7, 3 to 9. 2x plus 3. So I want to look for the inverse of this function. What do I mean by that is that anytime I put 5, 7, and 9, I want to be able to get 1, 2, 3, and 1, 2, 3 back. So therefore, all you have to do is that solve for x in this place. Make x the soluble formula. So therefore, you have in this place, you have y minus 3 equals 2x. If you divide both sides by 2, that implies that x is going to be y minus 3 divided by 2. And the implication of that is that your inverse function, f inverse of x, is y minus 3 over 2. So for now, if I say f inverse of 7, that would be 7 minus 3 divided by 2. What's 7 minus 3? That's 4 divided by 2. That's 2. So you can see that 7 is mapped back to 2. And that is how you find the inverse of a function. I'm going to leave you to do for the rest on your own. You can do that. So that is how you find the inverse of a function. And that's basically how we end the class on mappings and function. If you have not subscribed to the channel yet, you're not doing the right thing. Just click the subscription button, click the bell right away. I'll see you in the next one.